Good day, guys. Today, I'm going to discuss continuation of proving trigonometric identities using the fundamental or basic identities. So this is now number 6. Given cotangent of x plus tangent x equals cosecant squared x plus secant squared x all over cosecant x cotangent, secant x. Okay, so let's now have the proof. So again, we're asked to prove this identity working on one side only. I think better to work on the right side because the right side is a more complicated side than the left side. So let's copy that problem. I mean that part. So this is the side that we're going to work with. So our goal is to express this in terms of a sum of cotangent x and tangent x. So in order for this to express as a sum, we need to split this into two fractions. So getting cosecant squared x over cosecant x secant x. Okay? Then plus secant squared x over cosecant x secant x. From one of the laws of exponent, cosecant squared x, cosecant x. So one cosecant x is cancelled. So this is cancelled out. So minus 1 here. Same thing for the second fraction. Minus 1 here. Secant x is cancelled. Okay? So let's now proceed. So this is equal to cosecant x over secant x. The second fraction, we have secant x over cosecant x. From reciprocal identities, cosecant x is equal to 1 over sine x, while secant x is 1 over cosine x. And then here, so similar, we have 1 over cosine x, and in the denominator, 1 over sine x. So these are the identities of secant and cosecant x respectively. This complex fraction, we can express this as 1 over sine x times the reciprocal of 1 over cosine x. So that is cosine x plus 1 over cosine x times the reciprocal of 1 over sine x. So that is sine x. So giving cosine x for the first fraction. And then the second one, we have sine x over cosine x. From ratio identities, these are cotangent and tangent respectively. So for the first term, we have cotangent x. And then for the second term, sine x over cosine x, that is tangent x. So let's see. So this is already the left side. So we attain now our goal, okay? So that's it. So we have proven that this is really an identity. So let us have the seventh one. We have sine theta plus tangent theta all over cotangent theta plus cosecant theta. And this is equal to sine theta tangent theta. Okay. So let's see what we can do in this identity, and let's see if this is really identity. Let's work on the left side because this is more complicated than the right side. And our goal is to express this in the form of product of sine and tangent. Okay? So I'm going to express cotangent theta and cosecant theta in terms of, let's see, cosine and sine. No? Yeah. So, and also for this tangent, let me try this to express in terms of sine and cosine. So let's see what will happen. This is sine theta plus, so the identity for this is what? Sine theta, I mean, sine theta over cosine theta. Okay? So all over, so I think we need to move this so that the fractional bar will be at the middle of the equal sign. So getting in the denominator, I mean, is cosine theta over sine theta. Okay? Then plus 1 over sine theta. That is the reciprocal identity for cosecant theta. So this is now a complex fraction. Now to simplify this, we need to combine these two terms in the numerator as a single term, no? Meaning as one fraction. So let's do that. We have the LCD for this is cosine theta. So cosine theta times sine theta is equal to sine theta cosine theta, then plus cosine theta divided by cosine theta is 1 times sine theta. So that is sine theta all over cosine theta. And then in the denominator, so this is equal to the LCD of this is sine theta. So they have the same denominator. So all we have to do is to combine them. So getting cosine theta plus 1. Okay? So let me copy this because I'll be moving to the next slide. So take note of this right side. This is what we want. Sine theta, tangent theta. So how do we divide? When we divide, we multiply this numerator by what? By the reciprocal of the denominator. Okay? So the numerator is sine theta. Okay? And let's factor this at the same time. No? Cosine theta plus 1. And then over cosine theta. Okay, guys? So what did I do with the numerator of this complex fraction? So I factored out sine theta, giving sine theta and then the other factor, cosine theta plus 1. Then all over this cosine theta. And we multiply this by the reciprocal of this denominator. So the reciprocal is sine theta over cosine theta plus 1. So from which we can cancel this out. So cosine theta plus 1, cosine theta plus 1 here. So giving sine squared theta in the numerator and in the denominator, cosine theta. Actually, we don't need to combine these two as one, no? So just leave it as is. Sine theta over what? Over cosine theta times sine theta. Okay? And this is equal to sine theta times, and what is sine theta over cosine theta? So that is tangent theta. Okay, guys? Again, this is what? This is tangent theta, that sine over cosine. Okay? Then times sine theta. And that's what we want. So let's check. So that's it. So we're done. So we have proven that the given is really an identity. Okay? Now, by the way, this rectangle or this square here means that the proof has ended. Let's have number 8. So given 1 minus 2 cosine squared theta all over sine theta cosine theta. Okay? And that is equal to tangent theta plus cotangent theta. My copy is not clear. I'm not really sure if this is plus or minus. Because in the book that I am copying the problem, it's erased, no? So let us just check and change it in case this is negative or positive. Let's see which one is possible for this to be equal to the left side. Okay? So I'm answering problems without solutions. So I'm just copying from the book. This is taken from the book of Paul Ryder, Plane and Spherical Trigonometry. So we have the right side. Let's work on the right side. 1 over 2 cosine squared. Left side, I mean. 1 over 2, 1 minus 2 cosine squared theta all over sine theta. Okay? So let's work on this side. So let's see what do we have to do here. I want this to be a sum or difference because I like what I told you. I'm not really sure if this is plus or minus. We want it to be tangent, and then here, this is plus cotangent. Let us express one in terms of sine theta. So 1 is equal to sine theta 1. Sine theta plus sine squared theta. So let's see, sine squared theta plus cosine squared theta. Right? Is that incorrect, guys? Remember, sine squared theta plus cosine squared theta, that is equal to 1. Then minus 2 cosine squared theta. Okay? So let's see if this will work. And let's find out what will happen. All over sine theta cosine theta. Okay? So again, 1 is equal to sine squared theta plus cosine squared theta. Then minus 2 cosine squared theta. So let's simplify the numerator. We can combine this cosine squared theta and negative 2 cosine squared theta to get sine squared theta, then minus cosine squared theta. I think I'm now seeing what the sign here is. So this is supposed to be negative. So that is tangent theta minus cotangent theta. Okay, guys? So this is equal over sine theta cosine theta. And then let's split this into two fractions because we want this to be two terms, no? So that is sine theta quantity squared, then minus cosine theta quantity squared. So, but as I said, we need to split this, no? So for the first one, we have over sine theta cosine theta here. And then minus cosine squared theta over sine theta cosine theta. Okay? So here we can cancel one sign here and then minus 1. In the second fraction, I can have minus 1 here in this exponent and cosine is canceled. So getting for the first term, sine theta over cosine theta. So that's it. This is equal to tangent theta. And this one, cosine theta over sine theta. And that is equal to what? Cotangent. So we're done. So again, this is tangent theta minus cotangent theta. Okay? So this is really an identity. Okay? Because we are able to express the left side in terms of this right side. Let's have number 9. So we have sine theta plus cosine theta quantity squared plus sine theta minus cosine theta quantity squared, and this is equal to 2. Okay? So let's have the proof. Obviously, we have to work on the left side, no? Okay, let's express this as what? As 2. So we can begin, I think, by expanding, no? So let's expand each term. So this 2-term expression when expanded. So this is binomial in form. Although technically it's not binomial because it involves sine theta and cosine theta, not what you call this, not terms in a polynomial, no? So let's square this one. So square the first. So plus twice the product of the first and the second plus the square of the second. Then the next one plus the square of the first minus, so let's have it here, minus 2 times the product of the first and the second plus the square of the second. Okay? So from here, I can combine these two. So giving sine squared theta plus cosine squared theta. So what is what can you notice about this? So this is what? This is one of the identities in the Pythagorean identities, okay? And there is another set of that. So this one and this one. Let's put 2 checks. So I can write that as what? Plus, okay, sine squared theta plus cosine squared theta, okay? Then this term 2 plus sine 2 sine theta cosine theta is the additive inverse of this. So they, when combined, that is, they are equal to what? 0. Okay. So giving only this two group of terms, no? So the first one, so as what I mentioned before, this is very famous in trigonometry, no, or in trigonometric identities, as famous as what? Michael Jackson. Okay. So this is equal to 1. This is also equal to 1. So hence we have 2. And that's what we want. What we really, really want. Okay? So we're done. So it means this is really an identity. Okay, guys? Let's have number 10. So given sine squared theta minus cosine squared theta, it's sine to the fourth minus cosine to the fourth theta. So I think better to work with the expression involving higher power, no? So this involves a power of 2, while this one 4. So let's work on sine to the fourth theta minus cosine to the fourth theta. Okay? The way I see it, I think we need to factor this and consider this as difference of 2 squares. So the factored form sine squared theta plus cosine squared theta. This takes the form of a squared minus b squared. Our a is sine squared theta. Our b cosine squared theta. So we have a plus b, a minus b. Okay, that's it. So this is famous, no? And as famous as what? As famous as Isaac Newton, no? Yeah. So finally, we have sine squared theta minus cosine squared theta. Okay, we're done. This is very easy. No? Now, if you notice, so when working with identities, very important, your skill in algebra, no? So like, for instance, factoring, how to combine fractions, this will help. So aside from changing one expression in terms of its equivalent. Okay, so let's now have this 10th, 11th, this 11th one. Tangent squared theta minus cosine to the fourth theta, cosine to the fourth theta, and this is equal to, sorry, it's not cosine to the fourth. Let me check it. It is sine squared, no? And this is equal to product of same functions, but product. Something weird in trigonometric functions, no? So imagine this tangent squared theta minus sine squared theta is identical to the product, their products, instead, I mean, from difference equal to this product. So let's see if these are really equal, this left and right. Okay. We can work on any side, okay? I think they have the same level of, form, no? So let me work on the left side and express this as a product. Now, for this to be able to become a product, we have to express this as one term first, no? So to be able to express this as one term or one fraction specifically, you have to apply identity, I think, to the first one, no? To the tangent squared theta. In terms of what? In terms of possible, what's the possible? Is it sine squared theta over cosine squared theta or 1 over tangent? So you have those options, no? So which do you think? So let's try sine squared theta. Then if this will not work, well, then we can change this, no? Let's see what will happen if we change this to this form. Okay, guys? I can factor out sine squared. That is common. And then we have here 1 over cosine squared theta minus 1. Okay? And then I can apply identity to this quotient. 1 over cosine squared theta is equal to secant squared theta, applying reciprocal identity. If secant theta is equal to 1 over cosine theta, their squares are equal also. Okay? Then minus 1. But this is equal to what? This is equal to tangent squared theta, no? From Pythagorean identities. Tangent squared theta, then times sine squared theta. Okay? Product is commutative. So arrangement of factors is not important. So again, this is what? This is tangent squared theta. Then times sine squared theta. So giving what? The right side. Okay? So that's it. So let's now have number 12. We have sine to the 6x plus cosine to the 6x, and this is equal to 1 minus 3 sine squared x cosine squared x. Okay? So let's see. I think better to work on the left side because this involves higher power compared to the right side. The way you see it, we can treat this as sum of two cubes. Or possible, we express cosine to the 6 as quadratic cosine raised to 3. So let's see what the better option is. So let me try first the second option. So I will express cosine to the 6x as cosine squared x quantity cubed. And express cosine squared in terms of sine, and that is 1 minus sine squared x. Pythagorean identity, quantity cubed. So this is exponent 3. If you're going to expand this, the last term will give us negative sine to the 6, and it will cancel this. No, I think this will work. So let's proceed. So how do we cube a binomial form? So this is binomial in form, but technically speaking, it's not binomial, this inside expression. No? So how do we cube a two-term expression? So we have cube the first minus 3 times the square of the first. So square of 1 is 1 times the second plus 3 times the first. So 3 times 1 times the square of the second. So that is sine to the fourth x minus the cube of the second. So that is sine to the 6. Okay. So hence we can cancel this out. They are additive inverses of each other. So giving 0, the sum of these two additive inverses. We're left now with 1 minus 3 sine squared x plus 3 sine to the fourth x. We're almost close to the right side, no? So I'm going to retain 1 because there is 1 here. And then I have to retain negative 3 sine squared. So meaning I'm going to factor out this negative 3 sine squared x from these last two terms, no? So getting 1, let's copy this, minus 3 times sine squared x. So if I factor this out from here, so there is 1 left, no? And then here, if I factor out negative 3 sine squared, I will have just negative sine squared x. Okay? Yan. So let's check negative 3 sine squared x times 1. So that's negative 3 sine squared x. Negative, negative, positive. 3 sine to the fourth. Okay. Verified correct. So copy 1 minus 3 sine squared x. But this is what? Cosine squared x, right? From Pythagorean identities, of course. So that's it. So we have proven that the left is equal to the right. Okay? Let's have number 13. Cosecant and theta all over cosecant theta minus 1 plus cosecant theta all over cosecant theta plus 1. And this is equal to 2 secant squared theta. Okay? Obviously, left side is the side we what? The better to work with. So let's copy that left side. This is more complicated than the right side. Easier to put this in the form of this rather than this simple, going to be complicated. So minus 1 plus cosecant theta all over cosecant theta plus 1. Okay? This is equal to, so let's see what we can do here. Do I need to get LCD? If I'm going to get the LCD, let's see. So the LCD of these two fractions, cosecant theta minus 1, cosecant theta plus 1, okay? If I divide that by this, I will get cosecant theta plus 1, then times cosecant, okay? So cosecant theta times cosecant theta plus 1, okay? So by the way here, the LCD cosecant theta minus 1, cosecant theta plus 1. Okay? And then when this is divided by cosecant theta plus 1, that is cancel this part. And then this is what? This is multiplied to cosecant. So plus cosecant of theta multiplied to cosecant theta. Yan. Minus 1. Okay, that's it. Okay. Common cosecant theta, let's factor that out. So in the numerator, so what is left here? Cosecant theta, what? Plus 1 here, cosecant theta minus 1. Okay? After factoring out cosecant theta, common to each term in the numerator. So let's now make a fractional bar all over cosecant theta minus 1 cosecant theta plus 1. Let me multiply this out. So what's the product? So that is cosecant squared theta minus 1. A minus B, A plus B form. Okay? So I can now simplify this, no? Getting 1 minus 1, 0. So you now have 2 cosecant squared. Okay, 2 cosecant squared. So this is cosecant, sorry, 2, this is 2 cosecant times cosecant. So this is now 2 cosecant squared. Okay, guys? Am I correct? So this is cancel with this. So getting 2 cosecant times cosecant, 2 cosecant squared theta. And denominator, I can apply an identity for that. So that is tangent, that's cotangent squared. Cotangent squared theta. Okay? We're now close. We have 2. Let's manipulate cosecant squared theta over cotangent squared theta. So this is equal to 2 times cosecant squared theta, that is equal to 1 over sine squared theta. 1 over sine squared theta. Reciprocal identity. Let's put somewhere here. Then cotangent squared theta, that is equal to what? In terms of sine and cosine. Cosine is squared theta over sine is squared theta. Okay? So what we do here? 2 times 1 over sine squared theta, and that is multiplied to the reciprocal of this. Sine squared theta over cosine squared theta. Okay? Okay, now I can now cancel the sine squared and sine squared here. I will separate the two. 2 times 1 over cosine squared theta. Then finally we have 1 over cosine squared. That is secant squared. Oh, we have proven that, again, the left is equal to the right. Okay? So let's us now have number 14. So again, we have tangent theta plus tangent of 90 degrees minus theta. And this is equal to secant theta cosecant theta. Okay? So let's work on the left side. Tangent theta plus tangent of 90 degrees minus theta. So our goal is to express this in terms of secant theta cosecant theta. Okay? So for this to be able to be in the form of secant theta cosecant theta, we have to express tangent theta and tangent of 90 degrees minus theta in terms of sine cosine, and then later apply reciprocal identity perhaps. Okay? So this is sine theta over cosine theta. And then plus, we can apply here cofunction. This is equal to cotangent theta. Tangent of 90 degrees minus theta is cotangent theta. But what is cotangent theta? Cotangent theta is the same as cosine theta over sine theta. Okay? So this is cosine theta over sine theta. I'll get the LCD. We have the LCD is what? Cosine theta sine theta. When you get the LCD, divide by cosine. So I'll get sine times sine, sine squared. Similar here, no? Cosine sine divided by sine. That is cosine times cosine, cosine squared theta. So all over cosine theta, sine theta. Okay? The numerator is famous, no? As famous as what? Guys. As famous as Sir Isaac Newton. So this is equal to what? To 1, no? Equal to 1. Denominator, cosine theta times sine theta. Okay? So that's it, no? So if we express that as 1 over cosine theta times 1 over sine theta, so this is equal to what? Secant theta cosecant theta. Okay. That ends the proof of such. Okay, guys? Any question with that? Guys? Okay. So that ends our discussion. Hope to see you in the next video.